One more thing before we leave conversions, percent problems. If you're going to get something wrong, and I hate to put it this way, it might be this type of a problem. There's some little tricks that I hope to show you as we go through these. It says that the density of a solution of sulfuric acid is 1.285 grams per cubic centimeter, and it's 38.08% acid by mass. What volume of the acid solution in milliliters will you need to supply 125 grams of sulfuric acid? Anybody remember what the formula for sulfuric acid is? Yeah, it's H2SO4. All right, you don't really need to know that for this problem, but it's always good to review our chemical formulas. The density of a solution. What's a solution? Yeah, it has the acid and the water in it. So this is 1.285 grams of solution per cubic centimeter. Just to kind of remind yourself about that. And then it's 38.08% acid by mass. This is percent, part per whole. This means that there's 38.08 grams of the acid of H2SO4 per 100 grams of the acid solution. So of the pure acid, there's 38.08 grams for every 100 grams of solution once you mix it with water. And I don't think that's really clear from the onset of this problem. What volume of acid solution? So we want the volume of solution is needed to supply 125 grams of sulfuric acid. Now again, there's going to be several different ways that you can go about solving this problem. I like to start with what I know I have. Sorry about that, they're working out in the hallway. I know that I have 125 grams of sulfuric acid. That's what I want to come out with. So I start with 125 grams, and I will use the formula for H2SO4. That's what we want to come out with. Now we're going to set up the rest of our values so that we come out with a volume of solution eventually here. What factors could we use to get rid of grams of H2SO4? Yeah, we have here the percent of acid is 38.08 grams of H2SO4 for 100 grams of solution, but we're going to have to flip it. There's my grams of solution for every 38.08 grams of H2SO4. That will get rid of and cancel out the grams of H2SO4. Now we're in grams of solution. They want us to come out with volume of solution. We're in grams of solution now. How are we going to come out with volume? Yeah, here's our density of the solution, only it's in grams per cubic centimeter. To get rid of grams, I'm going to have to put the grams of solution in the denominator and the cubic centimeters in the numerator. That cancels out the grams of solutions. Now we're in a volume measurement. We're in cubic centimeters. Oh, but they wanted in milliliters. So here's that one factor to get rid of cubic centimeters and change it to milliliters. Now again, these are both volume measurements. We don't have to cube anything. 1 cubic centimeter is exactly the same as 1 milliliter. So we'll throw that factor in, and when you put it all together, it comes out with 255.45, and that's cubic centimeters. Now there's my answer, except that I haven't accounted for what? Sig figs, right. All right, so I'll go back here. We have 4 sig figs here. We have 4 sig figs here. And we have 3 sig figs here for my answer. So I really want to round it to 3 sig figs. 1, 2, 3, 2, 5. What do you think? What do we do with that? Yeah, we're going to leave it as a 5, and that's, oops, milliliters. You didn't catch me on that. Milliliters are the units. There's my final answer. I'm going to box it in, showing my setup with my labels for everything, and then the final answer boxed in here. Accuracy and precision. 2 words that unfortunately we almost use interchangeably, again in everyday language. The layperson, so to speak, if you ask them the difference between accuracy and precision, they might be hard-pressed to tell you the difference, but scientists view these 2 terms very differently. Accuracy is the agreement with the true value. The agreement with the true value. And I'll go over in just a minute exactly what I mean by that. That's accuracy. Precision is getting the same results as you do your measurement over and over again. The degree of agreement with several measurements. Degree of agreement with several measurements. All right, so if I weigh myself, I get on the scale and I weigh 150, and then the next day I weigh 150, and the next day I weigh 150, and the next day I weigh 150. I have a I'm being very precise. My measuring device is very precise because it gives me the same measurement over and over and over again. Now the problem is, if I really weigh 160, it's not very accurate because the true value of my weight would be 160 as opposed to my measuring device that keeps giving me 150 over and over again. So you need to be able to look at sets of data and tell me whether they're accurate, precise, neither, or both, and why. A lot of times we set up a bullseye chart to look at the differences between the 2, and this really helps me distinguish the difference between measurements that are accurate and precise. And hopefully it'll help you too. What's the object when you throw darts at a dartboard? What's the object? Yeah, to hit the bullseye. All right, to hit the bullseye. So we have 3 different bullseyes here, 3 different charts here that we're going to throw darts at. And the first one, I start throwing darts, and I don't know, however many darts I throw, they're all over the place. So do I have accuracy or precision? I'm trying to get in the middle here. Do I come close to the true value? No. Do I even get the same value over and over again? No. So this is neither accurate or precise. Now I start throwing my darts again, and here they go. Bomb, 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 bomb. All right. There they are. Hey, they're all together. Are they where I want them to be? No, so they're not accurate because it's not close to where I want it to be in the bullseye, but it is precise. I keep getting the same answer or the same result over and over again. It just happens to be the one that is not accurate. Now, if I throw them and they're over and over again on the bullseye multiple times, it's both accurate and precise.